Okay, it's 6 p.m. In Kiev, and I'm happy to open our webinar. My name is Olga Tarkhanova, and I'm CEO of Chemspace, and I'm very happy to welcome everyone at our today's webinar. The topic should be very, very interesting, and I'm looking forward to, first of all, to introduce our speakers to you, and then, of course, to listen to their talks, and then to discuss and to ask some questions. So the topic for today's webinar, the title for today's webinar is Real Fragments, Real Crystals, Integrated Fragment Discovery with Chemspace and SLS. Before we start and we actually come to our speakers and talks, I would like to remind you and actually maybe to present some general rules for our webinar. And first of all attendees at our webinar will be on mute mode during the whole webinar. The webinar will be recorded, and the recording will be accessible on our YouTube channel. So I encourage everyone to have a look at our YouTube channel. You can find a lot of very nice, very helpful information. And of course, maybe tomorrow, the recording of this webinar will be also available. We will close our webinar with Q&A session. And during this Q&A session, if you have some questions to one speaker or to another speaker, please type them in the corresponding section. So I will read these questions and then address the question to one of the speakers, and you're going to get your answer. And the third kind of thing I wanted to do today is also remind you what is Chemspace is. And Chemspace is basically a platform for discovering, designing, and delivering small molecules. So we think about our platform as an online platform and offline platform. So you can access our online platform, follow in any browser, follow the link chemspace.com, and you can run and surf within 18 billion of molecules using the different type of searches and easily order any of the molecules you can find. Doing this business, we also realized that some of our customers are in need to help us to help them to explore chemical space. So that's how our offline platform was launched. And now our offline platform consists of a few departments, like virtual screening department, artificial intelligence and machine learning department. We have chemoinformatics team, and we also provide chemistry and biology services through our partner Inami. Okay, and a few facts about Chemspace. So first of all, we've been on a market and the life science industry business for 10 years already. And for now, we have very successful business in terms of catalog business from our online platform, but we also put a lot of efforts to develop our offline platform. And this is very scientifically driven platform. So by now, we successfully completed over 100 discovery projects. We co-authored in more than 60 plus publications. And we keep working very hard to deliver to you very interesting solutions which could accelerate drug discovery process. So for today's agenda, we have 2 talks, and we're going to cover the following topics. So we're going to discuss about how we can use a real concept to accelerate the fragment-based drug discovery. And we're going to learn a lot of helpful information about Swiss light source. I'm very happy to introduce our speakers, Dr. Sharpe, She is a group leader at Macromolecular Crystallography Group at Swiss Light Source. She will cover the topics related how we can use the pipeline at Swiss Light Source for fast fragment and compound screening. She will present initial results from our joint project, which we already enabled, and she will provide some insights from the first data set collected on the upgraded SLS beamline. And our second speaker is Anna Kapeliuka. She is leading machine learning department at Chemspace, and she will talk about combinatorial spaces, about innovating real space, and how we can use combinatorial spaces to accelerate and improve fragment-based discovery. With that, I would like to kind of close my section, my introductory section, and give a stage to Dr. Sharpe. Welcome. The stage is yours. May?
I'm sorry. I wasn't sure. I wasn't aware I was going to talk first, but
oh, sorry.
No
it's my mistake. Yes,
no.
yes, that's right. Sorry, it's my mistake. Anna, could you please take over here?
Oh, yeah, sure. Sorry. Hello, everyone. I'll take a second to share my screen. Yep. It's gonna load. 1 second. Great. Can you see the presentation well? Okay. Great. So today we're going to be speaking about the real concept for integrated fragment-based drug discovery and what we at Chemspace developed to actually make this process easier. As some of you might already know, Chemspace specializes in exploration of ultra-large chemical spaces. And we specifically work with two of them, which are Inamine Real and Chemspace Freedom Space. Both of these spaces have synthon-based nature, meaning that the full molecule within the space is formed using synthons that are combined together in certain combinations. Why we keep promoting and using these two compound collections is because in their design, the developers tried and successfully solved the problem of synthetic accessibility. So for these two spaces, you can expect 80% plus synthesis success rate, meaning that your molecule will be actually delivered to you with a good chance. Besides that, these two spaces offer competitive pricing and fast lead times, which make them great for the hit identification stage. You can explore combinatorial chemical spaces in a lot of different ways. We have some examples here on the slide. Some of the approaches have been published, and it's a very active field of exploration. But we noticed a very distinct gap at the fragment-based drug discovery part because the fragment collections that are mostly present on the market, they are not tailored to be connected to these combinatorial chemical spaces. So we decided to fill in this gap by developing our integrated fragment-based drug discovery workflow. So it looks quite standard from the first point of view. So we start with the fragment hits, and we use those fragment hits to perform searches in the synthon space, in actual syntons of the Inamine Real and Freedom space. In these searches, we actually specify the exit vector in which direction we would like to grow our fragment, and we design specific subsets of these combinatorial spaces that have the fragment of interest that is expanded in the direction of choice. These custom sets are then scored by molecular docking and, of course, other methods that could go further. And these scored sets are used for hit selection. Afterwards, the compounds are being synthesized and biologically characterized. And this whole workflow can be fulfilled within Chemspace, besides the fragment screening, of course. But here we have a bottleneck, because what if we're not able to find the fragment hit in our space? And to solve this problem, we've set a task to actually design the libraries that will be compatible with the real concept and that can be efficiently used for the fragment growing purposes. To do so, we went ahead and had a look at the X real synthons, which there are more than 2 million of those, and we performed a very thoughtful analysis of this information. To do so, we developed 2 custom algorithms. One of them performs the exit vector determination in 2D coordinate space for the synthon, and the second determines the scaffold symmetry. Using these 2 algorithms and some sophisticated data analysis, we were able to annotate the parameters that you can see on the slide. And one of the most interesting of the parameters is the coverage score, which pretty much shows how many quadrants of this 2D coordinate space we can cover with our set of synthons for a specific scaffold. To make this concept more understandable, you can have a look to the right at the images. So let's say for the scaffold here, we have a set of synthons that cover these 3 exit vectors. These exit vectors are pointing into 3 different quadrants of the 2D coordinates, and this quadrant is not covered. So the coverage score for this scaffold will be 3. But in the scaffold below, we see only 1 exit vector, but the scaffold is symmetrical. So we're saying that this exit vector will cover actually 2 quadrants because of the symmetry of the scaffold. And using these parameters, we move forward and design the real fragment library. We started with 143,000 fragment-like molecules from the enamine collection of fragments. We overlap those with the Merca scaffolds within the enamine X real space and obtained 76,000 molecules. Afterwards, we filtered it down using our sociability principle and our annotation parameters to be left with 1,500 scaffolds, which correspond to 25,000 molecules. Afterwards, for each scaffold, we selected the representative fragments using pharmacophore-based clustering to ensure good pharmacophore coverage. And you can see from the UMAP here that even though we substantially decreased the number of scaffolds compared to the full space, it still covers this chemical space quite well, and the compounds are actually very diverse. So the final collection has 4,960 compounds. It is pre-plated, and it is already available from the website and has been used in projects with Chemspace. But afterwards, we thought that we need a specifically tailored library for crystallography because the throughput there is much smaller. So we utilized a similar concept, but applied a much stricter set of physicochemical parameters. And also a more sophisticated selection for the fragment per the scaffold, because here we also performed exact match and substructure analysis. So for most of the fragments, there's either a direct substructure in the synthon space or even the exact same synthon to the fragment. And the final library was also prepared using pharmacophore-based clustering, and it has 524 compounds. Again, both collections are pre-plated and can be already ordered from Chemspace website. And the coverage of chemical space here, of course, is smaller, but it's still quite great knowing that we have less than 200 Merca scaffolds. With that, I would like to show you how we use fragment growing within combinatorial spaces so that you can get the concept better and understand how you can apply maybe to your projects. So I'm going to show you a case study, which was done based on the crystal structures from the paper reference below. So here you can see the fragment crystallized in the pocket, and we used the same exit vector that was used in the paper, and we were able to find this synthon from which we were able to enumerate 24,000 compounds. So this was our custom set that we're going to use for docking. But besides the exact match, it is almost always possible to find synthon analogs, so slightly different fragments, synthons, that will help you to expand your chemical space and test your hypothesis. We can also integrate custom building blocks that are not found within the space, but can be integrated within the custom sets, which can be either bioisosters or some custom analogs of your compound. So here you can see the results of the docking. The docking is usually performed by using ICM Pro by MolSoft using an APF template. So we pretty much create a template around the fragment and we perform the docking. And here you can see some examples of the full molecules with good docking scores that originated from our fragment. A very similar concept can be utilized for fragment linking. So here in the crystal, we have two different fragments that we would like to connect. And we create the docking template based on both fragments and perform the docking of the custom real subspaces that are designed based on both fragments as well. And what was very interesting that in our top scoring compounds after the docking, we were able to find the exact molecule that the authors designed in the paper. So that was quite a nice finding because this whole case study took us less than a day to do. And there is one commercial project that we are allowed to show you, like the overview of it. So in this commercial project, we had one confirmed fragment hit. And based on this hit, because it was quite simple, we were able to design a library of 75 million make-on-demand compounds. Because this library was quite big, we used AI-accelerated molecular docking to explore this custom space. Afterwards, the top molecules underwent molecular mechanics simulations, and we selected 100 molecules for testing. Out of 100 molecules, we were able to receive the hit rate of 12%, with the hits showing single-digit micromolar activity. And on the image below, you can also see how we filled the pocket. So this was the shape of the fragment and then the final hit molecules. And also, I would like to say that because Black Friday is around the corner, we would like to offer 20% off on the fragment libraries as well as the fragment growing services. So if you would like to request that, you can use the code provided on the slide, and we will be happy to perform these projects for you. Yeah, thank you so much, and I'll be happy to give the floor to May.
Yeah, thank you very much, Anna. Thank you so much. And I think it was a great work you did, but the fragment-based drug discovery wouldn't so effective and so accurate if you won't have a crystal structure. Actually, our fragments with our targets. And yeah, Mike, the stage is yours. Thank you.
Thank you. Can you hear me okay? Can you see my slides? Okay.
Yeah. Yes.
Cool. Thanks. Well, firstly, thank you very much for the nice introduction, and also thank you for the opportunity to be part of this webinar. So today I'm going to talk about the fragment-based screening activities that we're carrying out at the Swiss Lightsource. So I'm going to start by just giving a very brief introduction to the SLS as well as the MX group. I'm then going to talk about our fragment screening pipeline, and I'm going to finish with a bit of information about our new upgraded beamlines and also the fragment screening campaign that we've carried out recently with the Chemspace REAL Crystallographic Library. So starting with an introduction. So for those who don't know, we're located in Switzerland, in northern Switzerland, about 10 kilometers from the German border. So the group is really responsible for running 3 protein crystallographic beamlines, plus a crystallization facility and our fragment screening platform, as well as, and we're mainly based in this round donut-like shaped building here, but we also run an end station across the river in the Swiss Valley. So these are statistics from before our upgrade, but we have about 2/3 academic users who come to the beamlines and about 1/3 industry users. And we have quite a large number of industry partners as well as regular industry customers. So let's moving on to fragment screening. I won't spend very long on this because I think most people probably in the audience know very much about this. But essentially, fragment-based drug discovery, or FBDD, is a productive alternative to traditional high throughput screening methods. So you can, rather than screening huge libraries, you can screen much smaller collections of much simpler compounds. And so it's a very efficient, expert way to explore chemical space. And the idea, as nicely illustrated in the last talk, is to find hits and then grow or link them to increase potency. It's a very established technique. It's been used for over 20 years in the pharmaceutical industry. It's also increasingly used in academia. And there's different ways of going about screening. One way would be to screen with a biophysical technique to maybe identify hits and then carry out crystallography on the potential hits. But it's also possible to use crystallography as a primary screen, and that's what we do here at the Swiss Light Source. And it works particularly well as a primary screen because you can work with really high concentrations of compounds, and so it's great for finding things with finding very weak binders like fragments, for example. So there's lots of advantages. You get very high information content. You can see, for example, if a fragment binds, you can see exactly how it binds, and you can then see how feasible it is for elaboration all in one experiment. But there are some disadvantages, mainly that you need hundreds or thousands of crystals, and each one of those is a separate experiment. So can be time consuming and also crystal consuming. But recently, technology really improved. I say recently, probably in the last 10 years, number of synchrotrons have set up facilities dedicated to carrying out crystallographic fragment screens, most notably XChem in the Diamond Light Source, and also HZB fragment screening facility, and Max4 and Fragmax at Max4. And this has really been enabled, I think, by changes and improvements in the automation speed of data collection at beamlines. So our project to set up our fragment screening platform started in 2017, and we call it the FFCS pipeline, or the Fast Fragment and Compound Screening Pipeline. It was kind of a name that stuck. So this started in 2017, and it was really implemented initially at the request of some of our beamline partners who wanted to have a fragment screening pipeline actually based at the SLS. And we've been in operation since 2019. And the approach we took when we set up the pipeline was to really look at all of the different stages of a fragment screening, the fragment screening process, right from crystal growth to soaking, harvesting, data collection and data processing, and then try and look really for like pragmatic solutions to each of these steps. So our goal wasn't to reinvent the wheel, but really just to find out good solutions which worked well for us. And the pipeline is primarily designed for industry projects, but we also do academic collaborations as well. So early on, when we were investigating what was needed for the pipeline, we realized that a really key component of this was the software. Because we're dealing with potentially thousands of crystals, thousands of fragments, you need to have a really nice way of very clearly linking all of this together. So we wanted a way of being able to track every aspect of the experiment, right from the crystal growth to knowing exactly how much fragment you added, which fragment you added, all the way to data collection and so on. So to address this, we designed some in-house software, and this is based around a MongoDB database and a PyQt designed GUI. We purposely chose a non-relational database because we wanted something with a very flexible schema. So the idea is that we are continuing to develop the software and add new features as we go. And essentially what the software does is it generates input files for our various hardware components in the pipeline, and then collects output files for all of the devices. So in this way, we can keep track of all of the experimental steps and components, from like the crystal plate, the cryoprotection, soaking and fishing and so on. And I'll show you some of those steps next. And I should say as well that this software was designed by two very talented software developers in the PSI at the time, Justina and Kuba. So this just gives an overview of the hardware that we use. We have a rock imager from Formulatrix for plate imaging. We use an echo for the ligand transfer directly to the crystal plate. We have a shifter for machine harvesting, and then obviously a beamline for data collection. And this is all of this is controlled via our central fragment screening database. But before you kind of even really start the experiment, you really need to have crystals. And this, I think, is one of the hardest, the sort of biggest bottleneck in doing fragment screening with crystallography. It doesn't matter how nice your hardware is and how nice your software is, you still need very good quality crystals. And the requirements of this are fairly high. You ideally want resolution better than 2.2 angstroms. You can go slightly lower, but the better, the higher the better. You need an accessible target site. And most importantly, you really need them to be very reproducible. So you know that every single crystal that you target is going to diffract well. And in order to utilize our setup, the crystals need to be stable at 20 degrees Celsius for the duration of the soaking part of the experiment. So it's possible to grow crystals at 4 degrees and then move them, but they can't be the kind of crystal form which then dissolves. And to address this, we have a crystallization facility also in the Swiss light source. And we have a number of staff members who are very expert in growing and optimizing crystals. So this is an example of endothiopepsin, which is the test case that we used for our nice collaboration with Chemspace. And this just gives an overview of a typical crystal plate. And endothiopepsin is a particularly nice target because you can really optimize the crystals very nicely. They diffract very well. They grow in almost every drop. But even in this case, you can see perhaps from this image, this is a UV image of a crystal plate, that not every drop contains crystals. And not every drop contains completely perfect crystals that you might want to target. So in the first step of our process, we needed a way of identifying which drops contain crystals. And to address this, we designed a piece of software called the XI GUI, or the Crystal Identification GUI. And it pulls images from our crystal plate from the rock imager. And then you can go through each image and you can just target it, and you can say, do I want to use this drop in these crystals for my experiment? And if I do, where do I want to target the drop? So you can go through all of your plates, and then you can send this information to the database. And then you can go to the main our main FFCS GUI, and then you can use this to control all aspects of the experiment. So you can really choose exactly, you can load in fragment libraries with all the information, the SMILES codes and so on, and compound codes, and you can assign exactly how much fragment you want to add to each drop. And you can do the same for cryo as well. And then once you've done this, you can then export this information. So input files are then readily available on both our Echo PC and also our Shifter PC, ready for the next step of experimentation. So yeah, at this point, the other thing you can use our software to design is exactly, for example, if you want to add a particular amount of solvent. So all of our libraries are stored in DMSO. So as a first step, we want to try and establish what the optimal soaking parameters are. And we use DMSO as a kind of a proxy for this. Because fragments are such often very weak binders, we want to try and work with as high a concentration as we can, and also to soak for as long as we can, to try and maximize the chances of seeing something bind. But the problem is not all crystals like DMSO. So you always have to kind of find the sweet spot between trying to go for as high concentration as you can and soak for as long as you can, but yet still have the crystals diffracting nicely. So the initial, for a new campaign, we usually spend at least couple of rounds of this, just really optimizing the soaking parameters, and also in combination with the cryo concentration if that's needed. And I should say here at this point, we also have an option in our setup that if your crystals really, despite lots of optimization, really don't like DMSO, or there's some reason that's not suitable, we also have a DMSO-free soaking method. And this was developed kind of early on when we were testing our pipeline. We had a user group from the University of Zurich, They had a very nice system which they'd been using for several years for soaking and so on. And we realized very quickly it wasn't compatible with our setup because the DMSO bound so strongly in their binding side that it blocked fragments from binding. So we found out a way around this. We dispense our fragments and dry them on the plate and then resuspend them using our crystallization buffer. It's not as ideal as the method of just injecting DMSO directly because you usually can't work with such high concentrations. But in our case, yeah, we were able to get 30 fragment binders from using this method. So then after that, after you've dispensed your fragments with your echo, and then you fished your crystals using the shifter, all of the results from these experiments are sent back to the database so that we've really collated every aspect. So we can see, for example, you know, was the soaking successful? Was the fragment dispensed correctly? What each fragment then will have a timestamp for when it was the soaking started. We then have another timestamp for when the crystal was fished. We can see, for example, how long it took to fish the crystals. So we really have an awful lot of information about all aspects of the experiment. And at that point, you can then export information on the data collection parameters, which you can then send to your synchrotron. So at this point, I would normally talk about our beamline straight away, but because we've had some changes, I'm going to leave that to the end. And talk a little bit about our fragment FFCS data processing pipeline. So this is a project from a postdoc in my group, Dennis, to design an offline data processing pipeline for all stages of processing, refinement, and ligand identification. And because for the last couple of years, the SLS has been undergoing an upgrade, we've actually had to do most of our data collection at alternative synchrotron sources. So we've designed our processing pipeline to ingest data from multiple different synchrotron sources and also multiple different formats, both CBF and H5 files. We then utilize our PSI computing cluster, and we really wanted to make the system as flexible as possible. So to be able to run multiple programs multiple times, to really try and customize it to fit your project. So it's the same for our whole setup. We try and design everything around the individual crystal and the needs of the crystal, because yeah, that's often the hardest bit to work with. Yeah, and then this is part of our same database, so we're able to retrieve and ingest the results of processing, and then we can filter and analyze statistics from the whole campaign and so on. So now I'm come to the last part of the talk, which is I'm going to talk a little bit about our SLS 2.0 beamlines as well, and also the Chemspace REAL Crystallographic Library screening project that we've done. Yeah. So this just shows an inside of our synchrotron. The picture on the left is actually how it's looked for some of the time, at least in the last couple of years. All of the insertion devices were completely removed. It was yeah, basically working in a kind of a building site. Over the last year, these were gradually rebuilt, and at the start roughly of this year, we actually had the first the light in the ring. And just to give an overview of like how we've redesigned our beamlines to make use of this improved storage ring. We have 3 protein beamlines. We have our PXIII beamline, and this is kind of our experimental beamline in a way. So we tried to make this as versatile as possible, have room temperature experiments, serial experiments, an end station which can then take lots of different sample formats, for example. We have our PXIII beamline. This is our industry beamline. The main goal of this beamline is to have it really robust and fast throughput, but also high energy, so we can collect small molecule data. And a PXIII beamline, and this one I'm going to show you in a bit more detail. This is also designed to be very high throughput, but also like our unattended queuing beamline. And the goal of this beamline is to really be used for our fragment screening operations. So this was the first beamline that was in operation in SLS 2.0, and we had the beamline had its first light in April of this year. You can see from the right side image that the beam is now much smaller and also with a higher flux. And it's really designed to be an autonomous beamline that's really optimized for drug discovery. So very fast data collection and a large number of samples per hour. And I have a video. Let's see if this works. You can sort of see a bit the beamline in operation. So that's our sample changer robot, our TEL sample changer, which is designed in-house. You can see now that it's mounted a crystal onto our gonio, and then it will carry out raster scanning, which it's doing now, just to locate the position of the crystal. Yeah, and then once it's done that, it will be able to detect where the center of the crystal is, or where the best part of the crystal to collect from, which it's doing now. It should be, and yeah, then it will now collect a data set in a very short time, and then the sample will be removed. So then the idea is that this can then really just run in a totally autonomous way with no user intervention, which is great for fragment screening because you have so many crystals. And at the same time, as the beamlines were upgraded, the whole space of our PXIII and PXIII beamlines was redesigned. And we built a dedicated fragment screening lab, which is just pictured on the right-hand side. This was about, I think we've had it now for about 11 months or so, nearly a year. And then this space is completely dedicated for fragment screening. And then this is our pilot project that we carried out in collaboration with Chemspace. So when we were, we decided it would be really good to have a pilot project when our PXIII beamline was back, to really collect a full fragment campaign. And this kind of the Chemspace project kind of nicely came together at the same point. So this was obviously a collaboration with Chemspace, but this whole project was initiated from our side by Alex Metz, who's now at UCB, and he's also an integral part of this project. So we decided to do a fragment campaign against endothiopepsin. Not the most exciting target, but it's a very nice test target. It's one that we've used before for testing our fragment screening pipeline. And the crystals diffract very, very nicely. And it's kind of like a sponge. It really just soaks up a lot of fragments. So you know you're always going to get a high hit rate, and that's really nice for then testing a new library. So we prepared our crystals using our fragment screening pipeline. We soaked everything at 30 millimolar final concentration in the drop for 3 hours. The crystals survived very nicely with this. The data was processed using Autoproc and Dimple, and then Phoenix Refine, and then we inspected it using both Panda as well as manual inspection, and then carried out additional rounds with Phoenix. The average resolution of our crystals was 1.2 angstrom, so really nice, high quality data. And we're still completely trying to confirm this, but it looks like we have about 138 hits out of all 524 fragments tested. And just below, you can see a selection of the different binding events. So the analysis of this is still a bit ongoing. But yeah, just want to thank really like the whole of the MX group. This is really, I think everything I've shown, all of the people here have been involved in some way or another. I'd like to thank the head of the MX group, Meitin Wang, the MX samples group. This is the group that I lead. This group is really responsible for running the crystallization facility as well as a fragment screening facility. Thank Dennis for actually being the person who prepared and harvested all of these 524 crystals. Also want to thank all of the software group, the applications group and instrumentation group, as well as the former group members who have been particularly instrumental in setting up our fragment screening pipeline. And of course, the collaborators Alex Metz, as well as Chemspace and Enemy. So yeah, thank you all for listening.
Yeah, thank you so much. It's very, very nice talk, very interesting talk. I learned a lot, actually. Yeah, we're very, very happy with our collaboration with this initial results of our kind of a screen of our library, and we are looking forward actually to get these results and perform this fragment growing Anya talked about today. So we are looking forward, and once it's done, I think we should call for the second round of the webinar. Okay, I think we could start a Q&A session. So I encourage everyone, please type your questions in the Q&A section, and I'll be happy to read them, and you're going to get your answers. So we have a few questions already. The first one, what is AI accelerated docking? I think it's for Anya. Anya may comment on this.
Yeah, it was mentioned on the slide from the commercial project. So in our case, AI accelerated docking is pretty much the use of active learning. Is a technique where a machine learning model is used like a surrogate for docking to reduce the time of exploring a specific compound collection. So pretty much we'll have a compound collection, let's say for 75 million. We take a small subset of it that will cover the whole chemical space. We dock this subset and we use this information to train a machine learning model. Because the prediction is much faster than docking, we can then use the predicted scores to guide the further selection of compounds for docking, and that is done in cycles so that we can better explore the chemical space, taking less computational resources.
Yeah, thank you very much. The second question, I think also, Anya, I'll ask you to address. Can I grow my fragment if I didn't use the library? I mean, library probably you presented.
Actually, yes. So the library was designed to make this process easier and like to ensure that your fragment will have good matches. But we can work with pretty much any fragments that are present in the crystal structures and try to find the available syntons in the space. But if we don't, there is also an option to use and synthesize a custom building block and integrate it into the space of choice to design this custom set that will be used for docking. That will be slightly more expensive because the building block will have to be synthesized for that. But generally, it's still very affordable and a nice way to go about this.
Thank you very much. And the next question to May. Could you please share which approaches you employ for protein crystallization? This is the first. And the second part of the question, do you mainly use vapor diffusion, or are there other methods you also find effective?
Okay, yeah, I'd be happy to answer that. So we do mainly use vapor diffusion, although we are actually also developing methods for using LCP, which will be published in the next few months. And my favorite technique to use is microseed matrix screening. So seeding techniques are really, really helpful when trying to get very reproducible crystals and optimize things too. I'd be very happy to send any publications about that if someone's interested. I meant to say as well, if people are interested in using the pipeline, both industry people or academic, please get in touch with me. And also, we also use the Chemspace screen. So if you'd like to use that for crystal screening, then you're very welcome.
Yeah, absolutely. Like from our point of view, so the library is accessible through Make-Room, and so if after the screen you may be interested in fragment growing, so Chemspace team would be happy to assist and to help. I think it's should be very good and very fruitful collaboration. Okay, the next question. Also to May, how many X-ray measurements can usually be performed on protein ligand complex before the crystal is no longer usable?
Okay. I guess it depends a bit on how you expose your crystal, I would say, and also how big the crystal is, because if you have a really massive crystal, you could expose one end of it and then center on a different part. Yeah, it's a bit hard to answer because you would need to know what transmission you were using. You can yeah, it would also depend a bit on the size of your crystal, I would say. So I don't feel like I could give a good answer that would cover all bases for that. It's very sample dependent.
And the next question, do you plan to collaborate with Chemspace in the future on the fragment growth campaign for the 38 hit fragments you have identified? I think all of us can say yes. It's what we're going to do next. Could you also kind of say on average how long it takes to enable the fragment screen for the new protein? For example, you don't have, let's say, like protocol for crystallization ready, so you just need to develop and then to perform the screening. So how long? What the timeline?
Yeah, answering questions about the hardest bit is just getting the actual crystals. And with all kind of crystallization experiments, it's almost impossible to determine like how long that will take. It will depend a bit on terms of the protein quality, or especially if the protein has been crystallized before by someone else. So it really depends. It can take anything, I would say, from like, if you're really, really lucky, a week to optimize your crystals, right through to months or years. It's quite hard. But there's certain things you can do to see, like I say, if your protein has been crystallized before, or similar proteins been crystallized before, that might give you a bit of an indication. But once you actually have the crystals, the process is quite fast. Then you need to carry out a round of optimization for the soaking parameters. And that, especially now we have the SLS back online, can take maybe a week or two. And then the actual screen itself would then take another week, I would say. But the really uncertain part is just how long it takes to actually get your crystals.
I see. I mean, so once you have the crystal, what you just mentioned, so the workflow is pretty much straightforward and can be accomplished. I would say it's that pretty much the same timeline as a usual high throughput campaign is actually done. Yeah, which is great. And another question, just about this kind of business model. So if you can, it would be also helpful for listeners to understand. I mean, as you said, for your part, you have this kind of crystallization. It's like the most challenging. It's probably you won't be provided any like exact numbers, something like AFT probably. And for the second part, is it also depends, or you may provide some kind of accurate cost for that?
Yeah, so if people are interested in the exact cost, then feel free to contact me. But for the actual, if you have a system which is already optimized, then the costs are very much more set. So we have a certain charge per every crystal that we soak and harvest and collect. So it's much more kind of clear cut. But we do also offer a crystallization optimization service. And then this is really costed on a sort of, depending on how many plates you need to carry out and how much time the experimenter needs to spend. So yeah, we what we typically do would be to say we agree a set of experiments up front to cost those, to do that, and then see where we are, see, you know, if it looks like the protein's going to crystallize nicely or not, and then do another round and so on. But yeah, it's a bit hard with that. It's hard to sort of say exactly how much it would cost.
Yeah, and also I think it's also worth mentioning that so if you run the project, that the customers they don't need to buy the library. So you have access to the library, and basically the price you're going to charge is going to include the cost of the fragments. It's going to include everything you just mentioned. So all this kind of screening activities as well.
Yeah, exactly. Yeah, thanks for clarifying that. Yeah.
Yeah. I do not have further questions. I think we also do not have further questions from our audience. And I would like to thank you. I'd like to thank May and Anna for very, very brilliant talks. And as I said, with Chemspace, we're very excited to have you on board and to have you as our collaborators. And we are looking forward that people will use the library for crystallization and for fragment screening. Yeah, thank you very much, everyone, for attending our webinar. And have a nice day, nice evening, whatever you are located. Thank you.
Thank you. Thanks.
Thank you.